Hello students, today we are going to study assembler functions and sic assembler. Okay, so now assembler. What do you mean by assembler? It converts assembly level language program into a machine level language. So assembler converts assembly level language program into a machine language. It means that assembly level language program is understood by human since it is a high level language program, whereas this machine level language program understandable by the machine, which is in the form of zeros and ones, and this assembly level language is understood by the human, which is in the high level language program. Okay, which is in the form of high level language program. Okay, so assembler converts the assembly level language program into a machine level language program. This assembly level language program is in the form of a high level language that is understandable by the human, whereas machine level language is understandable only by the machine since it is in the form of ones and zeros. Okay, so now we'll see basic assembler functions. Okay, basic assembler functions. So basic assembler functions, which means that translates the source code into a equivalent machine language. So which means we have a source program that consists of mnemonic opcodes and symbols. Okay, so this is one source program. This source program will be converted into a machine language equivalent through an assembler. So this is assembler, through an assembler we are converting. Okay, so we need to generate an object code as well. So this is the exact functions of an assembler. Okay, so what does it do? Translating mnemonics, so which means an operation code. Okay, mnemonics to their machine equivalent, machine language. And second, what it does to assign machine address, assign machine addresses to symbolic labels. Okay, this is what the basic assembler functions do. It translates the source program into an object code through an assembler. It means translating the mnemonic codes to a mnemonic codes or opcodes to their machine language. And second one, it assigns machine addresses to the symbolic labels. And we'll be saying number 3, this is number 2, and this is number 1. Okay, so next we'll see assembler directives. Okay, so assembler directives. Okay, so assembler directives are pseudo instructions. This is first point. And the second, this pseudo instructions, it means that they provide instructions. They The pseudo instructions provide instructions to the assembler itself. And they are not translated into machine operation codes. Okay, the pseudo instructions. So assembler directives are pseudo instructions. They provide instruction to the assembler itself. They are not translated to the machine operation codes. Okay. So now we will see what is an SIC assembler. What does it do? Okay. So here we are going to see SIC assembler. SIC assembler. So this SIC assembler converts into a machine language program. So the basic steps we need is, number one, we need an assembly program. Number two, we have to assign address. Number three, generate object code or object code generation. Okay. And number four, develop or create object program. Okay. Number one, we need an assembly program. Number two, we have to assign address to each instructions. Okay. For assigning address to each instructions. Number three, generate an object code. For object code generation, we need two things. One is address of instruction. Address of instructions. And second one is value of opcode. Value of opcode. Okay. And the fourth one is, after generating an object code, we will be creating or developing an object program. For this object program creations, we need three things. One is header record, text record, and the third one is end record. Okay, we will see this in the development of an object program. Okay, so when we go for an assembly level programming language or assigning address, we need to consider an addressing modes. We need to consider addressing modes that supports SIC assembler. Okay, so here we have direct addressing mode. Number one is direct addressing mode. Number two is indexed addressing mode. Number two, indexed addressing mode. Okay, so there are two addressing modes available. One is direct addressing mode and number two is indexed addressing mode. As we know, SIC assembler supports 24 bits. Okay, so SIC assembler supports 24 bits of instructions. We say 24 bits of instructions. Okay, so the instruction format could be how? So here we will have opcode X and here address. So address consists of 15 bits and X consists of 1 and opcode consists of 8 bits. Okay, so all instructions are 3-byte instructions. All instructions are 3-byte instructions. So here 15, 16, 24. Okay, so 3 bytes instruction, totally it consumes 24 bits. which means 1 byte is equal to 8 bits. Upper 3 bytes is equal to what? 24 bits. So it means 3 byte instruction, totally the instruction consumes or consists of 24 bits of instructions. Okay, so this is what the SIC assembler supports. Okay, so we'll move to how do we identify direct addressing mode and indirect addressing mode in an instructions. So when I say direct addressing mode, for example, we say okay, STL return address. So this is our an instruction which is in the assembly program. So STL return address. So STL is nothing but an opcode. We call it as mnemonic. Okay, and this return address we call it as label. So directly an opcode and a label. So we can identify this as a direct addressing mode. When we go for indexed addressing mode, so there is a technique to identify indexed addressing mode. So when there is an X which is part of an instruction, we call that instructions as part of the instruction itself. We call that instruction as indexed addressing mode. For example, we say LDCH buffer X, which means what? LDCH buffer X. So X is a part of an instruction. We say this is a index addressing mode. This is an opcode, a label, and X. X identifies what? Index addressing mode. Okay. So these are all the two addressing modes supported by the SIC assembler. Okay. Apart from these instructions, there are some assembler directives. Number 1, which is called start. Okay. Start is one assembler directive. End is an assembler directive. Byte is an assembler directive. And here RESB, reserve byte, word, and reserve word. These are all the assembler directives in an SIC assembler. So here start specifies the beginning of the program. Start specifies the beginning of the program. Okay, and end specifies the end of the program. End specifies the end of the program. Okay, for example, this end also can have the first executable statement. Example, so if I say end start, which means what? Okay, so end specifies the end of the program and this start specifies the first executable statement. So end also specifies the first executable statement, which means if you have a label with end, it specifies the starting of the program. Okay, so byte reserves 1 byte. Okay, which means reserves memory location or stores memory location. Okay, so here I'll make a note, executes first specifies end. Okay, also specifies first executable statement. For this is end start also specifies first executable statement. Okay, so here byte specifies or restores memory location, reserves 1 byte or stores memory location. So here reserve byte means what? It also reserves 1 byte, but during the execution time only we will be able to know the content. Okay, know the content, what it is stored in that reserved byte. Okay, during the execution time only we will be able to know the content, what it is stored in the reserved byte. Okay, and here word reserves 3 bytes. Okay, so word reserves 3 bytes, and again reserve word means what? Reserves 3 bytes but only know the content during the execution time, during the execution of the program. Okay, so this is how we use these assembler directives in a SIC assembler. Okay, so I'll tell you an example, explain you with an example, an instruction like copy, start, 1000. Okay, copy, start, 1000 is an instruction. So this copy is nothing but name of the program. Copy is nothing but name of the program. Program here means what? Assembly program. Okay. Start is nothing but start of the program. So this is an assembly directive. Okay. So start is nothing but what? Assembler directive. Okay. So it specifies what? Start of the program. I hope you are getting what I mean to say. Okay, and this 1000 is nothing but address of the program. Where to start? From this address you are going to start the program. Address of the program. So I do repeat, this is an instruction. Copy, start, 1000. Copy is nothing but name of the program. Start is an assembly directive, specifies the start of the program. Okay. So 1000 is nothing but address of the program. Where to start the program? In the 1000th location you are going to start the program. Okay. So all these addresses, all the addresses are represented in hexadecimal format. Okay. Hexadecimal format. For example, how do the address specify in an hexadecimal format? I'll tell you. So the starting of the program is 1000. If it is a 3 byte instruction, okay, so we are using here 3 byte instruction. Okay, so 1000. Okay, so each instruction have 3 bytes. Okay, so the starting of the program is at the location or at the address is 1000. If the first instruction uses 3 bytes and the second instruction starts at which location? 1003. It means what? How do it calculates? 1000 is one address, 1001, 1002. So here 1 byte, 2 byte, 3 byte. So 3 addresses, 3 memory location it's stored, and the next address starts from where? 1003, and again 3 bytes, so 1006. So 1003, 1004, 1005. So it uses 1 byte, 2 byte, 3 bytes. So 3 memory space it stores, and the third instruction starts at 1003, 1006, and next instruction starts at 1009. So 1006, 1007, 1008. So 1, 2, 3, and next instruction starts at 1000. So it moves on till the end of the program. So hexadecimal format in the sense what? So we start here 1000, 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, and next it starts from 100A. After 9, A, 100B, 100C, 100D, 100E, 100F. Okay, So after F, it starts from where? 1 0 1 0. Okay, 1 0 1 1, 1 0 1 2, 1 0 1 3, 1 0 1 4, 1 5, 1 6, 1 7, 1 8, 1 9, 1 0. What happens here? 1A. Okay, 1 0 1B, 1 0 1C, 1 0 1D, 1E, 1F. After 1F, how we'll write? 1 0 2 0, 1 0 2 1, 1 0 2 2, 2 3, 2 4, 2 5, 2 6, 2 7, 2 8, 2 9. After that, what happens? 2A, 2B, 2C, 2D, 2E, 2F. See this 2E, 2F and all you have to add here 1 0. Okay, 1 0, 1 0 and so on. Okay, like this you have to use the address in an hexadecimal format. I hope you understood this. Okay, so we will move on to the example of a program. Okay, we will take an example of a program. So this is the program. Okay, so here example program with object code. So you could have see the location LOC log, which means the address specified, source statement, which is the program, and the object code. So how does the object code created and all I will tell you, and I will tell you the purpose of the program. So these are all the programs here. Okay, so we have till here, see the continuation of the program and everything is till we have 2079 end first. I told you no, end. End means what? Specifies the end of the program. So if you have a label first, which means what? End first, which means this specifies the first executable statement. So what is the first? This is a label. So we have to check where the label available. So see, it is not available. And in this program, see, it is not available, not available, not available. We have to go for the further statements. See, it is not available. Label, where it is. We could find it here. Okay, so this is the label. So here we started and there we ended. Okay, so this is an object program. We'll see what is copy, start, first, everything. Okay, so I already told you copy is nothing but name of the program. So we'll write here name of the program. Okay, and start specifies, start is nothing but what? Assembly directive specifies starting of the program, and 100 is nothing but starting address of the program. Starting address of the program. Okay, so here in the, so starting address of the program is what? Here where it is starting. Okay, so first means what? First means the first executable statement. First means what? First executable statement. Okay, so here there is an instruction, which means what? STL. STL is nothing but an opcode. Okay, and return address is nothing but label. Okay, so STL return address, this is an instruction. Okay, so this instruction occupies 3 bytes. Okay, occupies 3 bytes, and the second instruction also occupies 3 bytes. Okay, third instruction occupies 3 bytes, and so on. Since it is a 3-byte instruction, the SIC assembler uses all the instruction, each and every instruction uses 3 bytes. Okay, so here this STL return address is a instruction occupies 3 bytes. So the starting address of the program is 1000. So it occupies 3 bytes means what? I have already told you how it occupies. 1000, 1001, 1002. So 1001 byte, 2 byte, 3 byte. So next address would be starting from 1003. So here you could see, okay, 1001, 1002 and 1000 all 3 byte occupies. Next is starting from 1003 and next it starts from 1006. Next it starts from 1009 and next it starts from 1000 C, which means what? 1009 one instruction, 1000 A and second instruction, sorry, not an instruction, 1009 1 byte instruction, okay, 1 byte memory space it's used, and 1000 A second byte and 1000 B, okay. So normally it consists of 3 bytes, okay, it occupies 3 memory spaces, and next instruction starts from where? 1000 C, okay. So after then C, 1000 F. After this F, how many bytes it occupies? 3 bytes. Again 1012. So 1000 F is 1 byte. 1010, no, second byte. 1011. So third byte. So it occupies how much? 3 bytes of instruction. So 3 bytes of memory spaces it occupies, and then it proceeds to the 1012 for the next instruction. Okay, so when you see all these instruction occupies 3 bytes of instructions. Okay, so when you come across here this statement 1039, so the previous thing 1036 occupies 3 bytes, 1039. What the instruction given here? Label. It's a buffer, okay, it's a label somewhere we used, okay. Reserve byte. You are going to reserve byte for what? 4096, okay. So this 4096 is an hexadecimal format. Instead of occupying 4096 memory space, we convert this hexadecimal format into a decimal, okay. So how do we convert this hexadecimal format into a decimal? How do we convert it here? Shall we convert it here? So 4096 we will be it is in the hexadecimal format. Hexadecimal format. So we convert it into decimal. So we'll write 4096 converted into decimal. So 256, okay, 0. And here again 16. 5, 1 so 16. Again we'll give 16. Again 1, 0. So see, in this we will be taking 1, 0, 0, 0. So instead of 496, the hexa format is converted into a decimal. We'll be getting 1000. So the 1000 memory space it going to occupy. After the 1000 memory space, we'll be starting a new address. So here 1139. It starts from here. Occupies how many memory space? 1000 memory space. So 1039. It is going to occupy 1000 memory space. So add it together 3902. Okay. So 2039 could be the next memory location for the instruction to be executed. Shall we see that? See here. Subroutine for read into the buffer. Okay. The next memory location is 2039. Okay, so far you have understood. I am stopping here. Let me tell you the purpose of the program. Okay, so we have seen the program and the it occupies the memory location 3 bytes. Okay, the purpose of the program could be, see, the purpose of the program is you are going to copy F1. Okay, so F1 is a device. Okay, and buffer you need to store the data. And now you are going to copy into a device called D5. Okay, I'll tell you. F1 is a device. So from this F1, you are going to read the data or transfer the data from this device to the second device D5. Okay. So I do repeat, F1 is a device. You are reading the content or you are transferring the content from one device to the second device, another device called D5. Okay, so when you transfer, you need a buffer to store the record or data. For that, you are using a buffer. Okay, so here for reading and writing, read from this device, storing into the buffer, and then you are writing the data to the D5. Appo read is one subroutine, write is one subroutine. In between, you need buffer to storage the data. Okay. So this is the concept of the program. You are reading a record or you are reading a data from F1 device and you are storing into a buffer. From the buffer, you are writing it to the D5. Okay, so this is the purpose of the program. But for in an SIC, for input and output operations, okay, or transaction, we need to know these two devices are ready or not. Okay, so before reading data from this F1 device, we check whether we test whether the devices is ready. If it is ready, we copy the record from here and we store it here. Okay, in the buffer. After storing, again we check whether this devices is ready to accept the data. Okay, from the buffer. So if it is ready, accept the data. If it is not ready, the record or the data will be keep stored in the buffer itself. Okay, after later when it is ready, it will be writing the data from the buffer. Okay, for reading and writing, we have two functions called read function, another one is write function. So we call it as read rec, which means read record, write rec, which means write record. Okay, so these are all the two functions we use to read the data from the F1 and write the data to the D5 device. Okay, so these are all the two functions we use. Now, how does the assembler assign address for the program? As I told you, assembler address the program with the 3-byte instruction. So, each instruction have 3 bytes. So, that also we see. Okay. So, here, and I told you, in an hexadecimal format, we converted and 1039 location, it uses 1000 memory spaces. So next instruction starts from where? 2039. So the next instruction we'll see here. See the 2039 it is starting. What were they doing in between? Subroutine to read into the buffer. Now you are going to what? You are going to read the record from the device. Okay. So all these object code and all these instructions we generated using the 3 bytes. Okay, when you come across, you'll know that how we used these 3 bytes and all. Okay, when you add it, you will be getting. Okay, fine. So the memory space here stored in like 0 till 999. Okay, so 1000 memory spaces we have used here. We have reserved 1000 memory space. Okay. Next we are going to see how do we assign, how do we not assigning, how do we generate an object code. Okay. So generation of object code. Okay, generation of object code. So we need a mnemonic table. Mnemonic table means what? Mnemonic is nothing but an opcode. So as I told you, mnemonics like STL is a mnemonic and JSUB is a mnemonic. Okay, and LDA, load accumulator, is a mnemonic. STA, store accumulator mnemonic, all these things are, and many more. These are called mnemonics. Okay, in mnemonic table we have mnemonics along with values. Okay. So these mnemonics along with values are given by the assembler while designing itself. Okay, so we see that, say I told you, STL, JSUB, LDA, compare, I mean JEQ, JSUB, J, all these things are mnemonics. So this mnemonic has values. Okay, that is designed by the assembler. Okay, that is designed by the assembler. So I'll show you. This is a mnemonics with the mnemonic code, I mean the value. STL 14 we have, JSUB 48 we have, LDA 00 we have. So we have mnemonics with the values. Okay. So now with the help of instruction and the mnemonics code, we are going to generate an object code. Okay. So we'll take one instruction. Okay, we see how do we generate. Okay, the first instruction STL. Okay, RETADR. STL is an opcode, RETADR. So we'll write here. Okay, STL. Okay, RETADR. So this is what? An opcode, a label. Okay, so this is nothing but what? Mnemonic or an opcode. So we'll see what is the mnemonic code for the mnemonic value for that. Okay, STL. What it has? 14. So we'll write 14 here. Okay, return address, RETADR. Okay, which means what? Label. So in an assembly program, we see RETADR. So this is the first STL return address, which means what? First program starting here, STL return address. So we have to search where this return address starts. Okay, so this is not 1000. So I mean a return address is not starting from 1000. First program, I mean the first instruction is starting from the 1000. So return address have some other memory space. We have to look on to our program where the return address starts. Okay. So return address, we will look on to the program where it starts. C loop, end fill, and label and all is available here only. Okay, you have to search end of the program 30, and here you could find return address. Okay, so you could see return address here. See return address. Okay, the address of the return address is 1033. So we will write this here. See, return address is 1033. This here where it starts executing. What it doing? Reserving one. Okay, reserving the word. Okay, it's going to reserve word. Okay, so the address of the program is what? 1033. That is what we are going to write it here. 141033. So now the object code is what? 141033 for the first instruction. Shall we see that? See, first STL. STL is a mnemonic or an opcode. Its value is 14. So here we have return, and the return address starts from 1033. Okay, shall we see second one? JSUB. Okay, JSUB RDREC. So mnemonic code of JSUB, the value would be what? 48. See, 48. So we'll write it here. I'll tell you. See, first we seen, second JSUB, the JSUB RDREC, which means read record. RDREC. Okay, so JSUB is a mnemonic or an opcode. What is the opcode value here? Opcode value is 48. So write the 48 here. Okay, read record is nothing but a label. We have to search where the label starts here. Okay, shall we search read record? So here the label starts. Copy first, C loop, and end fill, end of the file 3, and next is 0, return address length buffer. Okay, so we have not found here, and next page we will see. So read record. See, here you could find read record. What is the address of the read record starting? 2039. Shall we write it here? 2039. So we'll write 2039. So the second instruction would be what? 482039. Shall we see? See the second instruction. What? C loop. JSUB read record 482039. This is how we are generating an object code. Okay, any of the object code you take it. LDA3. Okay, LDA3. We'll take LDA3. LDA, what it is given? 3. Okay, shall we see? LDA as a mnemonic or an opcode. the value of the code could be what? LDA, load accumulator, 0, 0. Okay, so we'll write 0, 0. Okay, so 3 is the label of the program. We have to search 3 where it is available in the program. So 3 is a label. You could see the 3 where. So here you could find the 3. So what is this? Address could be 102D. So write it here, 102D. Combine it, 00102D. So this is an object code we generated. Found LDA3. See, LDA3 00102D. So this is how we are generating an object code. For this, no, nothing is, label is not specified here. So what we do, without if there is no label is here, you can simply put zeros. Okay, and 4C is nothing but what? R sub's mnemonic code. See, in mnemonic table we see R sub, the value is 4C. So R sub 4C. There is no label, so we replaced with the space 0, 0. It occupies 6 spaces. Okay. Am I clear to you? Okay, fine. See, 3. Word. Word just is a word. Word is nothing but an assembly directive. Okay. 3 is simply a value 3. So here for the assembly directive, nothing is to be specified. Just keep 3 here and rest of the spaces fill with zeros. Okay, and here word 0, nothing is going to be filled there on except 0. So word is an assembly directive, nothing, you just give zeros to be filled here. Okay, so reserve word 1, reserve word 1, if you don't have anything, you leave as such space, it is going to fill 1 only. Okay, here we have seen direct addressing modes like directly, STL, RD, RET, ADR, JSUB. Shall we see some indexed addressing mode which is available in the program? Okay. So indexed addressing mode, how do we identify indexed address mode? If X is a part of an instruction, we will say that it is an indexed addressing mode. So we'll see where is an X is a part of an instruction. See, we'll have LDA. This and all is a direct addressing mode. Okay. So there is in the second page we see. So subroutine to be read into the buffer. Next, okay, here LDX we have. Okay, LDX is a direct only. So when we go here, see, STCH buffer X. So X is a part of an instruction. So it means what? This is an indexed addressing mode. STCH buffer comma X. We'll search. See, LDCH. Okay. So LDCH buffer comma X, which means what? X is a part of an addressing mode. X is a part of an instruction. We could say that this is an indexed addressing mode. See, X is a part of an instruction. We say that this is an indexed addressing mode. Okay, so we'll see how to create object for this indexed addressing mode. So we'll take this example now. Okay, we'll write it here. What we have to write? STH. So our next example, STCH. Okay, buffer comma X. Okay, so X is a part of an instruction. We say that it is an indexed addressing mode. So we'll see the format. Instruction format could be what? Opcode X. Okay, opcode X. And what we have seen earlier, what is the instruction format? Opcode X address. Okay, that is what we are writing. Okay, so buffer address we are going to write. X means what? If X is a part of an instruction, we have to set the X denotes to 1, which means if it is an indexed addressing mode, we are going to denote this X to 1. If it is a direct addressing mode, it is 0, set to 0. And the opcode is like mnemonic or an operation code. Okay. So here, what is our opcode we have written? STCH. Okay. And X is, since it is an indexed addressing mode, we are going to set 1. Okay. And here, so we are going to set 1. And the buffer. Okay. the address of the buffer starts from where? Shall we see from here? Okay, this is the assembly programming, starting of the program. So buffer starts from, see here the buffer starts. So the address of the buffer is what? 1039. So we'll write it here, 1039. Okay, so this opcode occupies 8 bits. Here 1 and this one is 15 bits. Totally it has 24 bits of instruction. Okay, which means 3 byte instruction. Okay, 3 into 1 bit is 8. Okay, so 3 byte into 1 bit, which is equal to 24 bits. Got it? So it uses totally 24 bits. Okay, so this is in a what format? Hexadecimal format. The value of STCH is 54. Since it is an indexed addressing mode, we are going to set 1 and the buffer address is 1039. So shall we convert it? Since it is an hexadecimal format, we are going to convert it into a decimal format. So how do we convert this? Okay, we'll convert this 54 in an 8421 format. Okay, so 8421 format means what? 0 0 0 0 0 0 0 1 0 0 1 0. So adding 1 together you will be getting, add here 1 0 0 1 1, add here 1. So what do you get? 1 plus 1 10. Here 1 plus 1 10, 0, balance 1 1. Okay, 0. So this specifies 0, this specifies 1, this specifies 2, and this one 3, and this one 4, and again 0 1 0 1 specifies 5. Am I right? So write for 5 0 1 0 1. Okay, so make sure that you should have only 8 bits. Okay, for the 4, what you will write? 0 1 0 0 0 1 0 0. Okay, so 54 we have written like this. Okay, so check it is 8 bit or not. 2 4 6 8, 8 bit. So 1 we have to write as such. Okay, and 1039. So 1039, how do we write? So since it occupies 15 bits, so it should not exceed the 15 bits. Okay, so 1039. So start from here, 9. What is the value of 9 then? What is the value of 9? Shall we write it here? 0, okay, 1 0. 1 0 0 0. So this is 6, this is 7, this is 8. Am I right doing? 1 9. Okay, so 1001 is 9. We'll write it here, 1001. Okay, so we'll write it for 3. What it is? 0 0 1 1. Okay, so totally 1 2 3 4 4 8 bits. Okay, we have to occupy what? 15 bits only. Okay, so we have written 9, we have written 3, and next one is 0. 1 2 3 4. Okay, so we have written 0. So 4 8 12. Okay, only 3 bits have to be added for 15 bits. This buffer address specifies only 15 bits. Okay, so hexadecimal format, we are converting it into a binary format. So it has to occupy only 15 bits. From till here it occupied 12 bits. So again we have to occupy only 3 bit for 1. But obviously we have here 4 bits. What do? We'll write 0 0 1 alone we write. We have to start from here, 1 0 0. That's it. Okay, we have to use only this alone. We no need to write the previous one. Okay, so now combine it, 0 1 0 1 0 1 0 0. Okay, so what does it mean? 5 4. Okay, so combine from it here, 9, 3, take 4 bits, okay, 0, and this is 3 bits combined with here, okay. So 1009, which means 1001. What is 1001 here? 9. So we have to write 9. Okay, together you write it. 54909. Okay, so this is the address of indexed addressing mode instruction sic buffer x. Shall we check it in the object code? Okay, where it is? See, here in the object code sic buffer x. So what do we get? 549039. Shall we see? 549039. Okay, so this is an example for getting an indexed addressing mode. Okay, going to discuss how to write an object program. So we'll have a heading here, object program. Okay, so to generate or to write an object program, we need 3 things. One is header record. Number 1, header record. Number 2, text record. Number 3, end record. Okay. So to write an object program, we are in need of 3 records. One is header record, 2 text record, and third one is end record. So these records have their own templates. I'll tell you, to write header record, we have to follow certain things. Okay, so we have to follow what? Column 1. First column should be in the header H. Column 2 to 7, we have to write the program name. Column 8 to 13, starting address of the program. Okay, column 14 to 9, length of the object program. Okay, in bytes. So the program name should consist of 6 spaces, and this starting header should be in the hexadecimal format, and this also in the hexadecimal format. Second one is text record. To write text record, we have to follow these things. Column 1. Okay, column 1 should be the heading text T. Column 2 to 7, starting address of object code in this record. Okay, and this should be in the hexadecimal format. Everything is in hexadecimal format, but just specifying that. Column 8 to 9, length of object code in this record in bytes, hexa format. And column 10 to 69, here you have to write object code that should be represented in hexa format, 2 columns per byte. Okay, so totally it consists of 60 spaces. So mention it here, don't forget, 60 spaces. Okay, and the third one is what? To write the end record. So 3 records we have seen: header record, text record, and end record. End record, the column 1 should be specified, end record E, column 2 to 7, 2 to 7, you have to write what? Address of the first executable instruction. Address of the first executable instruction in object program represented in hexa format. We are going to write object program. So, object program. Okay. So, write an object program. Okay. So, we have to see all these instructions to be followed. So, to write an object program, we have 3 records: header, text and end record. So, in order to write all the object programs, we have to follow the instructions of header record, text record and end record. Okay. So, in column 1, what it says? The header record. You are specifying that first one is a header record. Okay. So, here in the column 1, you are writing H. Okay. So, to write each instruction's address and their object code, we need to separate between the 2 instructions. So, you are assigning here, you are going to write an header record H. So, next if I am writing a program name. Okay. So, what is a program name? We will take out that sheets, you know. See, what is the program name here? The program name is copy. Name of the program is copy. So, what it is given here? Next instruction is what? So, write the program name. So, in the column 2, program name is copy. So, you are going to write here COPY, copy. Return. So, totally the program name consists of 6 spaces. So, you have occupied here 4 spaces. Leave 2 spaces blank as such. Okay. So, in order to separate this column and the next column, we use a up arrow that is called a separator. Okay. So, what is the next? It has been given. So, after this 2 spaces, give a separator over here and column 8 to 13. So, 8 to 13 it holds again 6 spaces. 2 to 7 it holds 6 spaces. 2, 3, 4, 5, 6, 7. So, 6 spaces. 8 to 13, 6 spaces. What it is giving? Starting address of the program. So, what is the starting address of the program? Starting address of the program is 1000. So, write here 1000. 1, 0, 0, 0, 1000. So, it occupies 4 spaces and you have to prefix 2 zeros over here. So, now totally it occupies how many spaces? 6 spaces. Okay. Next instruction is what? Column 14 to 9. So, it occupies again 6 spaces. Length of the object program in bytes. Okay. So, length of the object program. So, have a separator over here. So, the length of the object program in bytes means what? So, how do you calculate length of the object program? So, you have to write, there's a formula called last address minus starting address. Okay. Last address minus starting address plus 1. Okay. So, what is our last address? Program's last address is 2079. See, the program's last address is 2079. Write it here. 2079 minus starting address is 1000. Okay. So, you will be getting 1079. 2079 minus 1000 is 1079 plus 1. So, what do you get? Will you get 1080? Is this the correct answer? Tell me, is this the correct answer? No. So, 1079. After that, what do you get? This is wrong. 1079 plus 1. 1079 plus 1. Next digit is what? 1007A. So, this would be your hexadecimal format. And here you have to write 1007A. So, this is how we create a header record. Okay, in an object program. We are going to generate an text record. So, in text record, what are the instructions we have to follow? We have to follow in the first instruction is we have to write T over here to identify this is a text record and starting address of the object code, length of the object code. So, we have written here, I have written here T to identify text record. Next one is starting address of the object code. So I have written starting address of the object code, that is a program 00100. Okay, the third one is what? Length of the object code in this record in bytes. So I have kept blank here. I will tell you how to generate the length. And next is what? Object code represented in hex 60 spaces. It means that you have to write object code to occupy the 60 spaces. So we have generated the first object code is 141033 for the instruction, the first instruction, first STL RET ADR. Okay, so this is 6 in digits. Okay, 1 2 3 4 5 6. So if it is 6 in digits, if we have 10 more object code, we can accommodate 60 spaces. Okay, so first record, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. Okay, so till here if we write the object code in text, we will be occupying 60. So 6 digits into 10 object code. Upper 6 into 10, 60 spaces we can occupy. So I have written 141003 here, and next 482039 here. So we have written till 10 objects code here. After, see here 10 objects code. So 00102D I have written here. Okay. So after this, what we have to write? So till here we occupied 60 spaces, and now we have to find length of the object code. So how do we find the length of the object code? So this is the formula: last address minus starting address plus 1. Our last address is what? 00102D. Where it is here? 00102D. So when we come across here, you could find 101B. It means that what? Starting address of the program for this instruction is 101B. After 18, we have 19, then A. Okay, so 8, 9, 1A. So these are all the 3 bytes occupied, and next starting address is 101B. It means that it is the starting address. So the instruction ends where? 1C, 1D. So 1, 2, 3. So we have to write here 101D minus starting address of the program 1000. So what do we get here? 1D. 1D, and this plus 1 will give 1E. So this is the length of the text record here. So we will write 1E. Next text record starts from here. So we have to identify the text record. We will be writing T over here, and where we stopped here, 00102D. Okay, next text record starts, the starting of the next instruction starts at 101E. So starting address of the object code in this record. So follow the instruction: starting address of the object code in this record. To write a text record, we will be writing next text record 00101E. And again you will be finding what? Length of the object code in bytes. So leave as such, and again we have to occupy what? 60 spaces. From where do we start writing the 60 spaces? 0C. Till here we have written first text record. See, we can have only one header record and as many number of text record we can generate till the program ends. Okay. So text record here is 0C1036. So we will be writing 0C1036 and 482061. So we write it till the 60 spaces it occupies. Okay, so we will write till the 60 spaces. After that we will be ending there. So when the program ends, finally what do? We write the end record. So write the end record. To write an end record, what we have to do? The column 1 specifies the E. It means that it is the end of the record. Okay, end of the program. Column 2 to 7, address of the first executable instruction in the program. So what is the address of the first executable instruction? So what is the address? Separator 00100. So address of the starting program. So this is how we will be writing the text record, header record and end record. To overall we will be saying this as an object program.